Hi, Robert hier. Dieser Podcast wird euch präsentiert von der Hannover Messe. Wir sagen vielen herzlichen Dank an die Kollegen in Hannover und jetzt geht's los. Robotik in der Industrie. Der Podcast mit Helmut Schmidt und Robert Weber. Hi, Robert hier. Das ist die letzte Folge vor unseren Sommerferien. Und wir haben uns dieses Mal bei den Kollegen vom Industrial AI Podcast bedient. Nämlich die hatten Rich schon vor einigen Wochen in ihrem Programm und der kam so gut an, dass wir gesagt haben, okay, nehmen wir Rich Walker von der Shadow Robot Company auch mit in den Robotik in der Industrie Podcast. So, Helmut und ich gehen jetzt in den Urlaub, entspannen uns ein bisschen. Der Helmut bleibt noch ein bisschen länger, der fährt nämlich erst Anfang September in Urlaub. Ich fahre jetzt in den Urlaub und wenn wir wieder da sind, gibt's was ganz Besonderes, was Neues vom Podcast Robotik Industrie. Wir wechseln nämlich die Seiten. Was das bedeutet, erfahrt ihr dann in der ersten Folge nach den Ferien. Wir wünschen euch alles Gute und bleibt vor allem gesund. Und jetzt geht's los. My guest today is Rich Walker. He works for Shadow Robot Company. And Rich, this is your second time as a guest on our podcast. Welcome back.
Thank you. A pleasure to be here as always.
Last time your cat played also a crucial part in the podcast. Is a cat also there?
He's at home today. I'm in the office, so we'll hopefully be spared the feline intervention.
Okay. How are you doing?
Oh, very good, very good. We've just finally released the new robot hand that we've been working on in secret for 5 years. So that's an absolute amazing kind of expansive rush, shall we say. And we're very excited to be able to tell people about it.
Exactly. All talk about AI and robotics. NVIDIA is making headlines with hardware, and so are you. So is hardware still worth it?
Oh, absolutely. I think what we've seen with the last 5 years of kind of advancements in AI is it's been totally driven by much, much better compute. Mm-hmm. NVIDIA's massive bet on GPUs as the fabric for doing deep learning has obviously really, really paid off for them. And for anyone who bought NVIDIA shares 5 years ago, well done. Well done.
Yeah. Congrats.
For the rest of us.
Do you have shares?
I did not in NVIDIA, no. Oh. Unfortunately, there we go. No, backing my own horse, I think. But for us over in the hardware, the kind of the deep tech corner, I think this is something we see that you don't get new hardware without a lot of work, a lot of development, but you do need to have new hardware to make things possible.
How much software and AI is in your new hand?
Remarkably little. We had a lovely relationship working with Google DeepMind developing this robot, and essentially they said, we're the AI people, you're the robot hardware people. Here's a little line. Let's not step over the line too much. And actually that was very, very rewarding because it meant that we didn't have to deal with the challenges they deal with. But equally, we could go to them and say, we have some ideas about our hardware designs. Do they solve this problem you have? And they go, yep, that will work and that will work. Let's do both of them.
What is now new? What's changing in AI and robotics at the moment?
Well, the change that we've been seeing is getting these kind of algorithms out of the video game and into the real world. We've seen lots and lots of examples where really powerful AI systems have been able to do really complex tasks, but almost entirely those are virtual tasks. Even if you could do them in the real world, they were done virtually. So even if you look at something like AlphaFold, which is predicting protein folding, but it's not then running the experiment to verify the protein folding, that's still got to be done by chemists. And what we're trying to do over in our little corner of the AI space is to say, well, okay, let's take these powerful AI tools and let's use them on real robots to solve problems that have been stuck for a long time in robotics.
For example?
So how do we pick up objects and interact with them well? That's a really, really big challenge in robotics. If you look at all of these very successful companies who do handling things with robots, if you look at what they do, they are very, very limited in the types of things they handle or the environments they do them in. Even the kind of world-class experts at handling objects at scale, like Amazon, are still operating in quite a restricted domain. Amazon expect the object to be on a shelf stack. Someone like Ocado knows that the objects will be presented in a warehouse. But when you get to, here's a random pile of things in your kid's bedroom, how do I clean them up? All of these systems just throw their hands up in the air and say, yep, can't do that yet.
You mentioned these all these AI algorithms, how do you integrate now? How do you combine both worlds, your hardware world and your AI algorithm world?
So a lot of that happens through a tool called reinforcement learning. Reinforcement learning is really powerful. Yeah. It's a method that allows you to take advantage of the fact that people have got really good at simulating physics.
I think Festo already presented a hand with a Rubik, I think, was it? Yeah.
Exactly. There have been quite a lot of interesting challenges where people have used reinforcement learning to solve them. But typically the problem you have is that, okay, you can do that in the simulator and it works really, really well. But then when you try and run those experiments in the real world, what happens is you break your robot.
Yeah.
And trying to keep the robots running for long enough to get these experiments done has been essentially the big showstopper here.
Yeah. And what is now your approach?
Oh, well, we spent thousands of hours beating the robots with sticks, so you didn't have to. Mm-hmm. Is the simplest way I can explain.
Mm-hmm. Mm-hmm.
For the new hardware, we said, okay, what reinforcement learning does is it tries random movements and works out which ones are good quality movements.
Mm-hmm.
So we have to be able to survive that. And then once we can survive that, what grasping and manipulation does is it collides the robot hand with objects. That's if I'm going to pick something up, my fingers are colliding with the object. By definition, they have to be to touch it. And traditionally in robotics, we avoid collisions. We say, oh, no, plan your path so you don't collide. But if you want to learn to handle objects well, you have to accept that collisions are going to be your bread and butter.
Exactly.
That we built a robot platform that was designed to survive quite hostile abuse. We hit it with pistons, we hit it with baseball bats, we hammered it into itself, and over thousands of hours of testing, we ended up with a platform that was reliable enough that could perform these experiments that really make you wince when you see a robot running on them.
So you're running the hand together with the robot, collecting data, or am I wrong?
Yes, exactly. The learning algorithm runs partly in simulation, but then translates across the real hardware. And when running on the real hardware, we have as much data as we can possibly get coming out of the robot. So this is something that people don't appreciate about classical robots, is they don't actually generate very much information. You might have some motor current data, and you might have some joint position sensors. And if you're really lucky, you'll have a force torque sensor at the wrist, and that's probably it.
Mm-hmm.
Whereas if you're trying to learn to understand acting in the real world, you want as much data as possible. So we've packed this robot with sensing to give you really, really deep insights into what's happening around the robot and with the robot while it's working.
And how much data do you collect, and what kind of algorithms now do you use then with the data?
So we have, I think it's something on the order of 155 sensors on each finger of the robot.
Each finger? But you still have 3 fingers, right?
3 fingers on this, 3 fingers. And then we have also video. Right? It's our previous hands were always very human-like.
Yeah.
So there'd be 4 fingers and a thumb, and the fingers would be that kind of characteristic up and down pattern that your fingers come in, and the thumb comes up to oppose those. This new hand is actually, it's only 3 fingers, but each one of those fingers is probably as agile as your thumb is. And they're arranged in a triangle, so they could do quite a lot of manipulation, quite a lot of dexterity.
Mm-hmm.
We could put more fingers there, but for the moment, 3 was enough to do interesting things and see what could be done and how we could do it.
Mm-hmm. And now you have this 100, you mentioned 150 sensors, right?
Yeah.
In one finger, right?
In one finger.
Okay, now you collect the data. And what is the next step then? What do you do with the data?
So for somebody doing research in robotics and AI, what they're typically doing with that data is they're taking it and they're feeding it they're capturing it while they're doing an experiment, and they're feeding it into their learning system.
Mm-hmm.
So that might be going in as real-time data that's used to generate control. You feed it into the neural network.
Mm-hmm.
The neural network generates commands back to the robot. Or it might be something where you're using a demonstration, and then at the end of the process, you're saying, okay, capture this data and learn from this data how to control the robot. And tools like, there are lots of the kind of good learning tools out there in the ecosystem now, like PyTorch and so on, that people are just kind of feeding this data into.
So, but this is not the reinforcement approach, right? This is how the hand behaves, right?
Well, the reinforcement approach
is the next step, right?
The simulation stage, typically, and then also on the real robot. But what the reinforcement system has to learn to do is to use both the images it's seeing of the robots in the world and the data from the robot to control its behavior. And of course, something that's very interesting is when you're simulation and your real robot have different properties. Sometimes this is called the sim to real gap because it's easier to do things in simulation than reality. But then on other occasions, we actually have more data available in reality because we can detect things that are actually very, very hard to model in simulation, and you're getting real live data from the world, from the interaction.
How many real life data does your hand need to see, or not to see, to, how do you call it?
Well, it's interesting. If you apply, we can go back to classical control approaches with this hardware. So typically internally, when we organize a demo, we're using maybe position control or joint torque control because we implement that on the robot for you. We're not trying to do the high-level learning systems, but if we are, or for people who are, they have all this extra data. So they have things like fingertip contact data, video streams from the fingers. There are IMUs, so you can measure vibration sensitivity. And then there are kind of the low-level information you expect, like the motor temperature and the motor current and things. Lots and lots of data, so you can you've got the ability to build a wealth of insight. Whether your algorithm ends up using it or not is up to you.
Okay. Can you, because we already talked about your new approach, can you please share some technical key facts? Is it an update? Is it a total new design? Some updates.
We went right the way back to a clean slate for this because we said to ourselves, we built anthropomorphic hands in the past. We've done lots and lots of those. But actually, maybe we don't care about anthropomorphism. We care about dexterity and reliability. And that turned out to be a different kind of lens to look at the problem from. So we were able to start and say, all right, what would a reliable robot look like? And where we ended up is this idea that you have a finger, and the finger has 5 motors in it, and those 5 motors drive 4 joints. That's a technique called N+1 actuation. Sounds a bit weird. Why have the extra motor? Turns out the extra motor means that you're never going through a period of zero force on any joint. So you never have backlash, which is really, really cute. The movements become, small, subtle movements become much easier to do and much more kind of flexible. So we have this modular finger design. We designed some new sensor control architectures, some new buses, and we kind of built all that into this package. It's bigger than our previous hardware. One finger weighs a little over 1 kilo. It's a really quite chunky object, but it's very modular. So you can swap a finger in and out without needing to change anything in your experimental setup.
And how fast is the hand to open and to close?
It's embarrassingly fast. We have some video where we're just like, wait, what happened? It's like you can't quite see it moving. If you're running it in torque control, it moves very, very fast. The joint control setting limits it to 180 degrees per second on any of the joints, which is a open and close in a second without too many problems. Yeah.
And how many Newton do you handle, or how do you provide for a fingertip?
So we were looking at this and saying to ourselves, do we want to build a reliable robot or a strong robot? Yeah. And okay, we could build a very strong, very reliable robot, but how big would that get? Yeah. And there's a certain limit which is going, okay, this is starting to get silly. So the spec that we came up with was to be able to handle, I'm going to call them typical objects, a couple of kilos in the fingers. So a 3-finger robot will hold 1 or 2 kilos without any problems. And across the working range, anywhere in the working range, it should be able to exert 8 newtons at the fingertip.
Okay. But what is your unique approach compared to other companies?
I think part of this is one of those projects where you go, well, actually, there's a whole stack of things going on that reinforce each other in the design. So we stuck to traditional actuation in terms of you just using top quality electric motors because we knew that would be a really good approach for us. From Switzerland. It's always from Switzerland. It's always from Switzerland. Absolutely. If you're buying motors and gearboxes and you're not buying them from Switzerland, please let me know. Yes. But then in other places, we were able to go back and say, okay, what's the right approach for doing this? And then often there wasn't a right approach. So we said, what are the possible approaches? And then we build a test program and work out what gave interesting information, what gave good data, what gave good performance, and go back to the researchers at Google DeepMind and say, hey, we see that there are 2 or 3 ways we can do this. Which do you like? And they would often say, we like all of them. Okay. And then we'd have to go back and say, okay, how do we put all of them in there? And that's why there are 2 completely different tactile sensing technologies in the hand.
I can order different tactile sensors.
We have different sensors in different regions. So if you look at your fingers, you'll see in the middle and proximal phalanges, you've got this kind of fleshy pad that comes into contact with things when you grasp.
Yeah.
And there we cover those with lots and lots of 3-axis Hall effect sensors with magnets. So really nice sensing technology, gives you a really good understanding of contact and deformation, and of course, in a compact form. It can be made over the surface of the finger. But then at the fingertip, we have more space available. Mm-hmm. So there we have a new sensor we developed, which is based on a stereo camera pair pointing at a pattern of markers on the inside of the finger, which is squishy. And as you squish it, you can see these markers move around. And we found that that's so sensitive that we've yet to have anybody manage to touch the fingertip without being able to detect it in the contact. But it's robust enough to go up to people pushing as hard as possible, 70, 80, 90 kilos of load on the finger. So newtons of load on the fingertip without it being unduly saturated. They're very, very responsive.
How do you achieve this technical accuracy of your hand?
So in that case, it was by looking at our options and trying them. And sometimes we said, actually, we're going slightly too far here. So we had a previous iteration of that sensor, which was so sensitive, it was clear that it was going to be really hard to process the data from it. And there we backed away a little bit. So we just have a high frequency video stream running down the hand to analyze. But then in other areas, there was kind of very obviously after a couple of iterations, it was clear that there was an approach that was excellent, and we didn't need to go beyond that. We could see clearly that was the right approach. It gave us the data that we needed. It gave us the reliability that we needed, and we knew how to build it, most importantly.
You mentioned DeepMind as your partner, as your customer, maybe. That's fine. That's a research company, a huge one. But Rich, how do you scale now your robotic hand?
Well, the nice thing about a deep research organization is that they will often buy quite a lot of hardware. Yes. So that's nice from a kind of purely technical point of view, commercial point of view.
Yeah.
But what we're very interested in now is saying, well, actually, what we've done is we've gone away and quietly over 5 years, we built a new category of robot hardware. What can be done with this new category of robot hardware elsewhere? Mm-hmm. What can you do when you don't mind if your robot hits things? What can you do when you've got the very, very high levels of dexterity and agility that a human hand has with reliability built into it? And what can you do with all this data that we're generating? So we're now going out and we're talking to the community and saying, how can we take this technology and how can we apply it into different places, different areas, different classical robotics challenges where so far no one's really used robots because they weren't quite good enough? Does this technology unlock good enough for you?
So how do you see the development of humanoid systems? Is that the new trend you want to follow?
There are lots of people doing humanoids.
Yeah.
I personally, we started out doing bipeds 25, 30 years ago. And we stopped because we realized that bipeds were too far away.
Yeah.
Now the world has changed. And, I think somebody pointed out to me that to build a humanoid from scratch takes 60 engineers a year.
Mm-hmm.
And it's almost quantifiable at that level. So we have some new technology. Is it potentially interesting for humanoids? Oh, I'm sure it is. Is it interesting for anyone else in the robotics community? Yes, I think so as well.
But you mentioned 150 sensors. That sounds very, very expensive for, I would say, common robotics applications.
It's true that we've done what Shadow always likes to do, which is to build the thing absolutely at the top of the mountain.
Yeah.
That's kind of where we always like to start. Are there simpler things that could be built? Oh, I'm sure there are. Are there ways to adapt this technology to be more general purpose? I'm sure there are. What we found very interesting was when we ran the hardware through our pricing model, it actually came out cheaper than our old hand.
Okay.
Which is a surprise.
How do you do that?
It's to do with the fact that the engineering was designed from the ground up for repair.
Okay.
And that turns out that repair and manufacturing in the first place are remarkably similar places. So something that's very fast to repair is something that's easy to strip down and put back together again. And that means it's pretty easy to put together in the first place.
So do you talk to our gripper providers like OnRobot, Schunk or Schmalz, or are they competitors and you don't want to talk to them?
Historically, we haven't, because we've just been operating in somewhere that's a very, very distinct location. Yeah. But now we are talking to more people who say, well, we have these products that we currently use. How does your new system fit into that landscape? And we're very interested to understand where we can contribute and where some of the technologies that we've developed may be able to make these like other types of hardware more versatile and more useful.
I want to come back to NVIDIA at the beginning, because the CEO says without AI in the design phase, and they won't get any further. What about you and your hand?
It's interesting that we didn't really use any AI in the design process.
But you collected during the testing, right?
Well, because what we were able to do was to essentially take some very bright people and lock them in a room and say, don't come out until you've got something that works. If you can afford that approach, it's a great one to take. In terms of future designs and future systems, I think one of the nice things is that we now know that we can use some of the tools from the AI toolbox to challenge our designs and to give us kind of things to explore for the next steps. Yeah.
Mm-hmm. But you are using simulation tools, right? You will use AI-based simulation tools.
We use the simulation tools, but they tend not to be AI-based. Something like Majocco or indeed NVIDIA's Isaac tool is a great simulator. They're very powerful, and they basically work off classical physics and just really good modeling of the classical physics, which is why they're interesting for AI, because they allow you to verify what the AI produces by testing it in a real simulator, a real physics model.
What is now possible with your hand? What are the plans of DeepMind? What they want to do? They want to do reinforcement learning with the hand. What else is possible with the hand?
I would love to know what they want to do. Honestly, we've been through this really great relationship where we built stuff for them and they went away and they came back and they said that won't work because. And we said, why not? And they said because.
Okay.
And we went, okay, fine, that's fair enough. They very much, they know what they want to do, and they have a strong focus on their particular innovations. And we're quite happy to sit here and say, okay, we're the hardware guys here. We don't need to actually understand the rigors of your learning systems algorithms, because what we need to understand is the rigors of your lab, where you beat the robot up and we make it survive that damage.
I want to come back when you said we want to also tackle different robotics application. How do I integrate the hand into my robotics system? Is it an API or is it a ROS-based operating system? What is your idea?
At the moment, it's all in ROS 1. We have a nice open framework where you have joint position control, joint torque control, tendon force control available. You have all the sensor data published in a nice big ROS topic, lots of ability using dynamic reconfigure to change the configuration of the system. But it's an open API in ROS. In fact, it's an open API in ROS 1. We've been joking that the entire project we've had moved to ROS 2, sort of in the middle of the to-do list. And it's now the end of the project and it's still in the middle of the to-do list.
Okay.
It's not been that critical to
You're a little bit late to the party, right?
Well, we have reliable, stable running systems that we run for thousands of hours on ROS 1. If we change them, we have to requalify. So that's part of the reason for sticking there.
Okay. So what are your next plans with your company?
Well, we're very excited to take this hardware out and say to people, what can be done with this? Where can it go?
Where can I buy it?
From us, from our website. Well, drop us an email. We're in production now. That's a really nice thing about this. We've actually transferred the production across to our Madrid team. So you can, if you feel the urge, just drive down to Madrid and collect one.
That's a European. Yeah.
Yes. we hedged our bets there.
And you produce in Spain, or where do you produce it?
Yeah, we produce it in Spain. Obviously, subcontract manufacturing happens all over the planet, but the final development, assembly, test is done in Spain at the Madrid office.
Rich, we wish you all the best with your new hand, with a new approach, with your new key customer, DeepMind. We learned that they order a lot of your robot.
More than most people do.
More than most people. It was a pleasure. Thank you very much and all the best.
Thank you, Robert. Pleasure.
Robotik in der Industrie. Der Podcast mit Helmut Schmidt und Robert Weber.